Hello students, in this lecture I am going to discuss the solution of the heat conduction problem by using the method of separation of variables. Now before we actually come to the method of separation of variables for solving the heat conduction problem, let me just discuss briefly what is the heat conduction problem. So in the heat conduction problem, what we do is that we consider a homogeneous rod of length L. So this is a rod of length L, and we are supposing that the rod is homogeneous, which means that the composition of the rod is uniform throughout. The material out of which the rod is made, that is the composition of that material is uniform throughout the length of the rod. Now the first assumption that we make about the rod is that the rod is sufficiently thin so that the heat is distributed equally over the cross section at time t. So we assume that the rod is not very thick, it is thin, so that the distribution of heat throughout the length of the rod, that is equal at any time t. Then the second assumption that we make about the rod is that the surface of the rod is insulated so that there is no heat loss through the boundary. So we assume that there is a insulation, or the surface of the rod is covered with some insulated material, or there is a insulation on the surface of the rod, so that there is no escape of heat through the boundary, which means that the rod can be maintained at a constant temperature because of this insulation. Now with these two assumptions, the heat conduction problem is given by this. It gives you the temperature distribution uxt of the rod. U actually denotes the temperature, and u is dependent on x and t. So u is a dependent variable which is dependent on the variables x and t. X and t are the independent variables. Here x denotes the horizontal distance at any point. If you are taking any point on the rod, then from the beginning it to that point it denotes the horizontal distance x, and t denotes the time. So with this, and u denotes the temperature when the horizontal distance is x and the time is t. So the temperature distribution uxt of the rod is given by ut. This is the initial boundary value problem that we have corresponding to the heat conduction equation. So ut is equal to k uxx, where x lies between 0 and L, and time t is greater than equal to 0, subject to two boundary conditions. These are boundary conditions because these are conditions on x. So when x is equal to 0, then u0t is equal to 0, and when x is equal to L, then ult is equal to 0. Now x is equal to 0 means that we are at this end, at the initial end. This is the end, x is equal to 0, and x is equal to L means that we are at this end. So when you are at the end, x is equal to 0, then the first boundary condition is that u0t is equal to 0, which means that the temperature at this point is 0, and when you are at the end, x is equal to L, then lt is given to be 0, which means that the temperature at this point is maintained to be 0. So at the endpoints, at the ends of the rod, the temperature is maintained at 0. So these are the boundary conditions. Then besides these two boundary conditions, there is a initial condition, which is here you are taking time t to be equal to 0. So this is a condition on time. So this is the initial condition, and we assume that at time t equal to 0, which means at initial time, when the time t is equal to 0, then the temperature ux0 is given by fx, where x lies between 0 and L. The horizontal distance x can be between 0 and L, where L is the length of the rod. So this gives the initial temperature, and the initial temperature is given by some prescribed function fx. So this is the initial condition. So one initial condition is there, two boundary conditions are there, and this is the heat equation. So this is a heat conduction problem, and it is a initial boundary value problem corresponding to the heat conduction equation, because boundary conditions and initial conditions both are given. So now we have marked this equation as 1, and we want to solve this initial boundary value problem using the method of separation of variables. Now in the method of separation of variables, we assume that the solution uxt is of the form xx into tt, where capital X is a function of small x and capital T is a function of small t. Also, we are looking for a non-trivial solution of the heat conduction problem. We are looking for that value of u which not only satisfies the heat conduction equation, but it also satisfies these initial conditions and these boundary conditions and initial condition. And we are looking for a non-trivial value because the trivial solution or the zero solution u is equal to 0 is trivially a solution of the heat conduction equation. So, in short, you are looking for the solution u which is of the form u is equal to capital X into t. So, now what we do is we put the value of u is equal to x t, which we have marked as 2 in the first equation of the problem 1. So, putting the value u is equal to x t in the first equation is u t is equal to k u x x. Now, when you put the value of u as x t over here, then ut means that you are differentiating u partially with respect to time, and the value of u is equal to x t, and x is a function of small x and t is a function of small t. So, this is del by del t of x x into t t, and now because this particular portion does not contain the in the variable t, so this will be treated like a constant. So, x x or x capital X just comes outside, and inside you are left with del t by del t. So, this is what you have. This is x, and t we know is a function of this capital T is a function of small t only. So, this del can be replaced by d. So, this partial derivative actually becomes the total derivative, and you can write it as x t dash. So, this means that the value of u t comes out to be x t dash. So, this is the value of u t. The value of u t we have substituted over here x t dash. In a similar manner, u x x is calculated, because u x x means that u x x is the partial derivative of u with respect to x 2 times. Twice we are differentiating partially, and if you put the value of u as x t, so this would mean del square u by del x square, del square x t by del x square, and again t, this capital T does not contain the variable x, so it will be treated like a constant. So, this comes out to be del square x by del x square, and again because capital X is a function of small x only, so this partial derivative actually becomes the total derivative. So, this is d square x by dx square, because capital X just contains the variable small x, and so we can write this as t x double dash. This total derivative of capital X with respect to small x differentiated 2 times can be written as t x double dash. So, we have replaced the value of u x x over here, this value, by t x double dash or x double dash t. It is one and the same, and this k is as it is. So, this is the final equation that we have after substituting the value of u is equal to x t. And now, bringing the terms of x on one side and bringing the terms of t on one side. So, we divide by capital X over here, and here we bring k on this side and we bring t on this side. So, this equation becomes x double dash by x, all the terms of x are on one side, is equal to 1 by k t dash by t, and these are the terms involving small t. This form of equation that we have got, this form is called the separable form, because we have been able to separate the terms containing the variable x and the terms containing the variable t. So, this is a separable form, and here we can see that the left hand side is a function of small x only and the right hand side is a function of small t only, and the two sides are equal. Now, this is possible only when each side is equal to a constant. So, let us suppose that that constant to which each side is equal is minus alpha square, and minus alpha square is purposely being taken so that we can reduce the solution later on in a simplified form. Although this is our choice how the constant is taken. This constant is called the separation constant. In some derivations, the separation constant is also taken as lambda. Here purposely we have taken the separation constant as minus alpha square, just to bring a solution in a compact form. So, from here we have two equations. One equation comes by equating the part of x with minus alpha square, which means x double dash by x is equal to minus alpha square, and the other part comes by equating this this term or the right hand side, the terms involving small t with minus alpha square. So, this is the second equation that we have, and now writing these equations in a compact form, you can just bring everything on one side, take x over here and then bring these terms on one side. So, this is the final equation that we have, x double dash plus alpha square x is equal to 0, which we have marked as 3. Again, bringing all the terms of capital T on one side, you have this denominator you can bring on the other side, and then this gets multiplied. Finally you can bring all the terms on this side. So this is the final equation that we have, T dash plus alpha square kt is equal to 0, which we are marking as 4. So these are two ordinary differential equations that we have. This equation 3 is a ordinary differential equation of second order in x, and equation 4 is a ordinary differential equation of first order in t. So now transformation that we have made is u is equal to xt, and this value has been used so far only in the first equation. This particular equation is the first equation, and we have used the value of u is equal to xt in this equation. And now let me use the value of u is equal to xt in the rest equations. These are two boundary conditions, and this is the initial condition. So I just use the value u is equal to xx into tt in the first boundary condition. The first boundary condition is u0t is equal to 0. So this means that the value of small x has to be put equal to 0 wherever it occurs. So I put the value of small x as 0. So this u is actually uxt, and when you put x is equal to 0, we put x is equal to 0, you get u0t, and the value of u0t is 0. So 0 is equal to u0t is equal to x0. We are putting the value of x as 0 over here into tt. This is equation 5 that we have. Again using the value u is equal to xx into tt in the second boundary condition, ult is equal to 0. So this u is again explicitly, if we write u is a function of x and t, and here wherever x is coming we replace x by L, and so ult is equal to 0, 0 is equal to ult is the boundary condition, and here when you put x is equal to L, this comes out to be xl into tt. This we are marking as 6. If we take a look at 5, here from 5 you have that x0 into tt, x0 into tt, which is this expression, comes out to be 0. Now this product will be 0 if either x0 is equal to 0 or tt is equal to 0 for any arbitrary t. Now if you take tt to be equal to 0 for any arbitrary t, then this would simply mean, if tt is equal to 0 is being taken to be 0, this would simply mean that this value becomes 0, and because this value becomes 0, the whole product becomes 0, and so the value of u would also become 0. But we are not looking for 0 values of u, we are looking for non-trivial solutions or non-zero values of u. This means that you cannot take tt is equal to 0, because that this value is of no interest to us. We are not looking for 0 solutions, we are not looking for 0 values of 0 value of u, we are looking for non-trivial solutions or non-zero values of u. This means that the only possibility left is x0 is equal to 0. So that is what we have taken over here, that from here you have that x0 is equal to 0, and then again considering the second equation here, from here we get a relation that xl into tt, this is equal to 0, xl into tt, this is equal to 0, which means that because this product is 0, so either xl will be equal to 0 or tt will be equal to 0. And now if tt is equal to 0 for any arbitrary t, then uxt, which was taken to be product of xx into tt, this will also automatically become 0 if tt is equal to 0 for any arbitrary t, which means that uxt would become 0. But this is not a solution of any interest to us, because we are looking for non-zero values of u or non-trivial solutions. This means that tt is equal to 0 for any arbitrary t or for all t is not possible. So the only possibility that we are left with is xl is equal to 0. So equations 5 and 6, so from 5 and 6 we get that xl is equal to 0, x0 is equal to 0, and xl is equal to 0. So these are the two new conditions that we have, and these two new conditions that we get, we are marking them as 7. So this means that what do we have in hand with us? We are basically looking for non-trivial solutions or non-zero values of x. We are interested in non-zero values of capital X. Why? Because we are interested in non-zero value of u or non-trivial solutions u, and u we know is a product of x and t. We have assumed our solution to be of this form. So if you want u to be non-zero, then obviously x should also be not equal to 0, and t should also be not equal to 0. So we are looking for non-trivial values of capital X and non-trivial values of capital T. So we are looking for non-zero value of xx, we have a non-trivial or a non-zero value of xx is a solution of the problem. This is the problem that we have to solve, and we want a non-trivial value of capital X. So the problem is x double dash plus alpha square x is equal to 0. This is the same differential equation that we got over here when we reduced our partial differential equation. This is the partial differential equation that we have ut is equal to ku xx, the heat conduction equation, and this got reduced into two ordinary differential equations. One was the differential equation in capital X, which is given by 3, and the other was the differential equation in capital T, which was given by 4. So this is the differential equation we are concentrating on right now, which is the differential equation 3. We will come to the differential equation 4 also once we have found out a non-trivial or a non-zero value of x. So basically what we are looking for is we are looking for a non-zero or a non-trivial value of capital X, which is a solution of this ordinary differential equation of second order in x, subjected to these two conditions which we have just obtained: x0 is equal to 0 and xl is equal to 0. This was numbered as 3 and these two conditions were numbered as 7. Collectively I am numbering them as 8. So now let me try to solve the problem 8. Now we consider the problem 8. Now in the problem 8 we consider this particular ordinary differential equation 3, which is x double dash plus alpha square x is equal to 0. Now x double dash means that you are differentiating capital X 2 times with respect to small x. So x double dash can be written as d square x by dx square plus alpha square x is equal to 0. This is as it is. Now this is a second order ordinary differential equation and you have to solve it. So this second order ordinary differential equation, generally actually we are in the habit of representing d by dx as capital D. So this d square by dx square, this can be written as d square x plus alpha square x is equal to 0, and this can be written as d square plus alpha square. This is nothing but an operator. D is an operator, the differential operator, and it is operating on x is equal to 0. In a way, in layman's language, you are taking capital X outside. Now this is the expression that you have which involves the differential operator D. Now to solve this particular ordinary differential equation of second order, what we consider is the corresponding auxiliary equation. To find the corresponding auxiliary equation, we consider this expression d square plus alpha square, and in this expression we replace d by m. So what the auxiliary equation is m square plus alpha square is equal to 0, or m square is equal to minus alpha square, or the value of minus this in fact can be written as minus 1 into alpha square, and the value of minus 1 is I square, where I is iota. So this minus 1 is replaced by I square, so I square into alpha square, and from here we find out the two values of m, or the two roots of the auxiliary equation, and the two roots of the auxiliary equation are plus minus I alpha. So we are getting complex values or complex conjugates, and now m can be written as 0 plus in the form of a proper complex number a plus plus minus ib, where a is the real part and b is the imaginary part. So it is written in the form of a complex number. So the general solution of the differential equation, this is the differential equation that we were trying to solve. So the general solution of this differential equation is because there are two values of m that we have obtained, correspondingly in the general solution there will be two parts. So the general solution is given by, the general solution of the differential equation 9 is given by xx, this is equal to e to the power 0x, 0 is the real part over here, into a cos alpha x, the imaginary part, plus b sin alpha x, where a and b are arbitrary constants. Now this is a rule which of writing the general solution which we learn when we study the ordinary differential equations. Here a and b are arbitrary constants. E to the power 0x is e to the power 0, which is 1, and so this 1 we are not writing. So xx comes out to be a cos alpha x plus b sin alpha x. This value we are mentioning as, we are referring to this value as 10. Now use the first condition x0 is equal to 0, which is given in problem 8 in equation 10. So which means that I have to replace wherever, because this stands for small x, so wherever x is coming you have to replace it by 0. So 0 is equal to x0, here I replace small x by 0 and we get 0 is equal to x0. This is the condition. This is equal to a cos 0 plus b sin 0. A cos alpha 0 is 0 and b sin alpha 0 is again sin 0. So sin 0, the value of sin 0 is 0, so this term just vanishes, and cos 0 is 1. So 0 is equal to a. So the value of the arbitrary constant a comes out to be 0. Now using this value of arbitrary constant a over here, so this term also vanishes, which means that xx comes out to be b sine alpha x. This we have marked as 11. Now using the second condition, xl is equal to 0, which was given in the problem 8. So which means that I have to replace this small x by L. So I replace this small x by L and I get XL, and but XL is 0, and 0 is equal to B sine alpha L. So this is the expression that we have. Now this expression is a product of two expressions or two terms. So since this product is 0, this means that either B should be equal to 0 or sine alpha L should be equal to 0. But if you take B to be equal to 0, then if B is taken as 0, then the value of B, when you substitute over here as 0, this expression, whole expression would become 0, which means that the value of capital X would come out to be 0, and this is not what we want, because we are looking for non-zero values of capital X or non-trivial values of capital X. But if you take B as 0, the value of capital X becomes 0. This means that you cannot take B is equal to 0. So this means that B is equal to 0, this value is B is equal to 0, this value is not acceptable. So we take B not equal to 0, and if we are taking B to be not equal to 0, this means that the second expression or the second term sine alpha L, this should be equal to 0. So sine alpha L comes out to be 0. Now whenever sine theta is equal to 0, this means that theta is equal to n pi, where n can be 0, plus minus 1, plus minus 2, and so on. So this alpha L is playing the role of theta. So alpha L is equal to n pi, where n is equal to 1, 2, 3, and so on. Now you can just see over here that I have not taken n to be equal to 0. N can't be 0 over here, because if you take n as 0, then this product would be 0. And if this product comes out to be 0, then alpha L will be 0. But as far as alpha L is concerned, alpha L is non-zero. Why alpha L is non-zero? Because alpha is also non-zero and L is also non-zero. L stands for the length of the string. So L is non-zero, and as far as alpha is concerned, alpha is non-zero, because if you remember, alpha comes in picture from at this point when we were able to reduce the equation in separable form. So here if you take alpha as 0, here suppose I take alpha as 0, then in that case x double dash by x, this is equal to minus alpha square, so this would be equal to 0, and which means that x double dash would come out to be equal to 0. If you integrate, you have x dash is equal to and if you integrate again, you with respect to small x, you get x is equal to ax plus b. And if you put small x, because we have a condition over here that x0 is equal to 0, this is one of the condition that we have just used. So when you put small x as 0 here, when you put small x as 0, and here this capital X is a function of small x. So when you put small x as 0, the left x is actually a function of small x. This is what we have. If you put x is equal to 0, this term will vanish, and this left hand side would also be 0, which means that the value of arbitrary constant b would come out to be equal to 0. And when you put back the value of b as 0, then this xx would come out to be equal to ax. And again, there was a second condition that we had in hand with us, that the second condition was xl is equal to 0. So when you put x is equal to l over here, put x is equal to l over here and over here, from here you get, on the left hand side you have 0, and on the right hand side you have a into l. Now if the product a into l has to be equal to 0, this means that either capital A should be equal to 0 or L should be equal to 0. But as far as L is concerned, L is non-zero, because L is the length of the string. This means that capital A should be equal to 0. This means that both the arbitrary constants capital A and capital B are coming out to be 0, which means that the solution x, this particular solution x, becomes a 0 solution, and we are not interested in the 0 value of capital X. So if you take alpha to be equal to 0, then capital X would come out to be 0, which is not something which we are interested in. So alpha can't be equal to 0, so alpha is non-zero. So here we have that alpha is non-zero. So because alpha is non-zero and because L is non-zero, so that is why n cannot be taken as 0. So, n is not equal to 0, because if you take n is equal to 0, then the right hand side would be 0, which is not possible. So, n is equal to 0 is not being taken. Also, you can see that we are not taking the negative values of n. We are just taking n to be 1, 2, 3 and so on. We are not taking n to be minus 1, minus 2, minus 3 and so on. There is a reason for that, and we will come to that reason later on. Now, for each value of n that you take, for whatever value of n that you take, you get corresponding value of alpha. So, that is why there is not one value of alpha here. Actually, alpha comes out to be n pi by L, but the value of n's are going on changing. You are taking n as 1, you are taking n as 2, you are taking n as 3 and so on. So, corresponding to each value of n that you take, you get a value of alpha. So, there is not one value of alpha that you obtain, there are infinite values of alpha that you obtain, and these values of alpha we are denoting them by alpha n. So, for every value of n, we obtain a alpha n, which is given by n pi by L. This equation I am marking as 12. Now, using 12 in 11 was this equation. 11 was given by the equation which gives you the solution xx is equal to b sine alpha x. So, putting the value of alpha over here, this is the value, this is 11. So, when you put the value of alpha, this was 11, xx is equal to b sine alpha L, alpha x. So, when you put the value of alpha as alpha n, where alpha n is given by n pi by L, then for every value of alpha n, you have a arbitrary constant, and corresponding to that arbitrary constant, you have a solution. So, there is not one arbitrary constant b that you obtain, or one solution that you obtain. There are infinite arbitrary constants, and so infinite solutions that you obtain, and that is why we are representing the arbitrary constants by bn and the solutions by xn. So, this is the value of xn that you have. Xn is equal to bn sine, I put the value of alpha n over here, n pi by L into x, and we are marking this as 13, where n is equal to 1, 2, 3 and so on. Now, from here you can just see that even if you take n is equal to minus 1, minus 2, minus 3 and so on at this point. So, because I know that sine minus theta is same as minus sine theta. So, even if you take n as negative, the negative sign will come out, and finally the negative sign will just affect the arbitrary constant. So, as far as the magnitude or as far as the form of the solution is concerned, the form of the solution will not change. The sign will just affect the arbitrary constant. So, as such, the solution doesn't change. The sign gets absorbed in the arbitrary constant, and the form of the solution remains same. So, no new values are obtained. So, which means that there is no need to take n as minus 1, minus 2, minus 3 and so on. These are all superfluous values. They are taken care of when you take n to be 1, 2, 3 and so on. So, here bn's are arbitrary constants, and now so, this is the final solution that you have, the final value of xn that you have. The final value of xn is given by bn sine n pi x by L, where n varies from 1, 2, 3 and so on. So, this is the final solution or the final value of the function capital X, which we have marked as 13. Now, coming to the function capital T, whose non-trivial values again we were looking for. Now, there was a second differential equation that we had obtained, which is the differential equation of first order in capital T, and that was T dash plus alpha square kt is equal to 0. Now, again we solve this ordinary differential equation of first order. You can just write it in a simplified form. T dash is actually dt by dt plus alpha square kt is equal to 0, and this d by dt, this differential operator in short can be written as d. So, this is dt plus alpha square k t, this is equal to 0, and this can be written as d plus alpha square k. In a way, you are taking t outside, t is equal to 0. So, now corresponding to this particular expression, you can write the auxiliary equation by replacing d by m. So, the auxiliary equation comes out to be m plus alpha square k is equal to 0. Now, the value of m or the root of this auxiliary equation comes out to be m is equal to minus alpha square k, and correspondingly the general solution of this differential equation comes out to be T is equal to c e to the power minus alpha square k. This is the value of the auxiliary of the variable m. This is the value of this m. So I put the value of m over here into t. So this is the solution that you get for this particular ordinary differential equation. This discussion again comes when we learn ordinary differential equations, when we learn the solutions of ordinary differential equations. This is the rule for writing the solution. So we have obtained the value of t, and now we have to put the values of alpha. The values of alpha that we have obtained so far, there is not one value of alpha that we have obtained infinite values of alphas. So alpha n came out to be this was the expression here. The values of alpha n's are given by this 12. Alpha n is equal to n pi by l. These are the values. So there is, as I was saying, there is no one value of alpha that you have obtained. You have obtained infinite values of alphas or alpha n's, where n is equal to 1, 2, 3 and so on. So alpha n is equal to n pi by l. Now these values are substituted over here. So t comes out to be, again for every value of n there is a value of arbitrary constant. C here was the arbitrary constant. So for every value of n you get an arbitrary constant, which we are denoting by Cn, and again then on the left hand side also you get a for every value of n correspondingly, because arbitrary constants are there changing, and the value of n changes. So correspondingly we get a new solution each time. So these solutions are denoted by t and t. So there is not one solution but infinite solutions that you obtain corresponding to each value of n that you take. So these solutions are given by t, and t is equal to Cn. Putting the value of alpha n's are n pi l this whole square. This is t and t is equal to Cn e to the power minus n pi l whole square kt, and this we are numbering as 15. So here Cn's are arbitrary constants. So we have obtained the value of Tn also. We have obtained the second function also, and the first function xnx, that was already obtained. Now just putting the value of Tnt and xnx, this is the value of xnx in u is equal to xt. So u is equal to xt was the solution that we had assumed at the beginning, but there is not one value of x and x that we have obtained, and there is not one value of t that you have obtained. The values of x's are infinite, and we have obtained xn. These are the values, infinite values, which we are denoting by x and x, and there are infinite values of t that we have obtained, which is t and t, and now substituting their values over here in xnx and tnt, correspondingly you will get infinite solutions of the form un xt. So this is the value of xnx that you have, bn sin n pi x by l, and this is the value of tnt that you have given by this. I am just using 13 and 15 here. We are using equation 13, which was marked earlier, and here I am using equation 15. Equation 13 was giving you the value of xnx, this equation, and equation 15 was giving you the value of tnt. So we have substituted the values over here, and un xt. Now these two arbitrary constants, this product can be considered, b and cn can be considered as another arbitrary constant, small a n, and there is a term of the exponential term which I am writing first, and then there is a sine term. So this is the solution that we have marked as 16, where a n is equal to b and cn is an arbitrary constant. Now all these are infinite number of solutions that we have obtained for n is equal to 1, 2, 3 and so on. Now because the heat equation which is ut is equal to k uxx, this is a linear and a homogeneous equation. So sum of solutions of this equation will also be a solution. So since all these are solutions, so sum of such solutions will also be a solution. So the solution of the heat equation, which is in the form of series, or a series solution, can therefore be obtained, and that is given by sum of all the solutions. So uxt is a solution in the form of a series, and this is given by summation un xt, n varying from 1 to infinity. So we put the values of un xt from here, from equation 16, u and xt are given by this. So this is the value that I am using, this whole value I am using from 16, and we are marking this equation as 17, which is in the form of a series. Now there was one initial condition also in the problem in the beginning, ux0 is equal to fx. Here t was taken to be equal to 0, which we have not used so far. So using this particular initial condition, which means that wherever t is coming, you have to put t as 0, wherever t comes, put it as 0. So in 17, so using this particular initial condition, fx is equal to ux0 and putting t as 0. So here we have put t as 0. This was the expression for t, and in rest there is rest expression, there is no term of t. So fx comes out to be equal to e to the power, this whole product becomes 0. So this will be e to the power 0, and e to the power 0 is 1. So here you are left with summation n varying from 1 to infinity an sine n pi x by L. That is what you have. So now this particular expression that we have obtained, this value of fx that we have obtained, where fx is a predefined function, fx can be represented by a Fourier sine series. This series that you have obtained is a series containing only sine terms, and this is in the form of a series called Fourier series. So if one wants to read more about Fourier series, one can always go and read a book in analysis and find out more about Fourier series. But this is a expression in the form of, this series is in a series in the form of a Fourier series. So fx can be represented by a Fourier series if these coefficients are Fourier coefficients given by an is equal to 2 by L integral 0 to L fx sine n pi x by L dx. So for this series to represent a Fourier series, the Fourier coefficients are given by this. So these are the values of the coefficients an, and now just substituting the values of these coefficients an in the solution. The solution was given by 17. So using the value of ans over here, the ans are Fourier coefficients. Using the value over here, we have uxt comes out to be summation. So here we will substitute the value of an. So we substitute the value of an. This is the value of an. This is the value of an, although in an we are writing x over here, the term of x is being written over here, but since you have a definite integral 0 to L are the limits, so instead of writing x, you can even write tau, because I want to differentiate between the x which is inside this bracket and the x which is outside the bracket. So I am writing this small x by some variable, let's say tau. So this whole thing represents an, and I am representing, instead of x I am taking x, instead of this x I am taking tau, because inside the definite integral it hardly matters what you are writing, whether you are writing x or tau, whatever, it's one and the same. So and these expressions are as it is, the way they were in 17. There is no change in these expressions which are outside an. These expressions are e to the power minus n pi by L square kt into sine n pi x by L. So the same expressions are written over here, the same expressions. This is only the value of an. So this is the final solution that we have obtained for the heat conduction equation, and this solution is in the form of a series. So this is the series solution of a heat conduction equation. The given problem involving the heat conduction equation, the problem 1 which involves the heat conduction equation with the two boundary conditions and one initial condition, and this solution is called the series solution. So that was all about the solution of heat conduction equation using the method of separation of variables.